Our next speaker is Jeffrey King. Jeffrey King is Associate Professor of Metallurgical and Materials Engineering at the Colorado School of Mines. His PhD is in nuclear engineering from the University of New Mexico. And Dr. King's research includes nuclear reactor design and analysis, and he is a regular presenter at the annual Conference on Nuclear and Emerging Technologies for Space. Just last year, he co-authored a cutting-edge article in the journal Nuclear Engineering and Design, examining a quote-unquote moderated low-enriched uranium kilowatt-class space nuclear reactor. So without any further ado, Jeff King.
Thank you, Al. Thank you, Alan. Oh, that does not sound like it's working. So I got to just stand up and go to instructor voice.
Outside voice.
Yeah, outside voice, classroom voice. So while they're pulling it up, so in addition to this, something like 20 years ago, I was working at Savannah River as a tank farmer. And I decided that was about the time that Savannah River went through the first series of layoffs, and it became a part of our job duties to go find another job. That was literally added to our job description. So go find somewhere else to work. And I decided at that time that I wasn't really happy being a tank farmer, it was not what I wanted to do with my life. And I started looking at grad school. And as in part of that looking, I ran into Mohammed El-Gang at the Institute for Space Nuclear Power Studies. At the time, there were two major space nuclear power institutes in the United States, one at the University of New Mexico and then another one at the University of Florida. They're both, INSPE, which is one in Florida, is gone. ISNPS is still around, but they're not doing nearly as much in space. But I bring that up because it was the space power focus and the opportunity to do things in space that really brought me into nuclear power. And it was the thing that got me excited. Since then, I've done a lot of other things. I still keep my foot in space power, but I've done projects in safeguards and security. We've done projects. Right now, my biggest project actually is additive manufacturing for nuclear power systems. But we still keep into this one. And I should start off by acknowledging the graduate student who did most of the design and analysis, or most of the analysis, Ms. Leonardo Mancarini, who was with us at the Colorado School of Mines for 3 years. And this was the analysis was his project. So,
Should we use the clicker?
yeah, let's try and use the clicker.
Well,
there's a full screen mode.
Okay.
We go into full screen.
Yeah. We're in full screen.
Yeah, and this is a shame. How did I send you the wrong copy of the presentation? All right, well. Yeah, let's skip that one and that one. Let's go to space nuclear power options. I must have sent you, yeah, one. All right, so if we look at past and future space nuclear power, so certainly we've been talking about space nuclear power since the 50s. The United States has launched one space nuclear reactor. Soviets launched 30 some odd. And like I said, it was what brought me into the space nuclear world. It's the reality that if we're talking about manned missions to Mars, if we're talking about manned missions on the moon, nuclear power is a necessary component of that. And likely nuclear power becomes becomes enabling, and it becomes necessary to go to a reactor versus an RTG. An RTG is a plutonium-238 power source that can get you to about a kilowatt. If we want above a kilowatt, we're looking at much higher power sources. So we look at past development, and space nuclear reactors in the past, typically developed by governments, typically developed by governments that were nuclear weapon states. So the United States, Russia, maybe a little bit China, and a little bit the European Union. So at that point, HEU was definitely the logical choice. You're not worried, in a sense, if you already have nuclear weapons, you're not worried about that country developing nuclear weapons using the HEU technology. and certainly was in the middle of the Cold War. If we look towards the future, though, there's an interesting thing that's happened, and that's that we've gone from an environment where it's governments and nuclear weapon states to now we're starting to talk about commercial development. We're talking about countries that are not nuclear weapon state wanting to get into the game. And I actually am fairly encouraged by that. 10 years ago, if you'd asked me if we were ever going to have commercial space flight, I would have said there's no chance that would ever happen. Nowadays, we have a Tesla Roadster on a long orbit around the sun. So clearly there's interest, and you hear the rumblings in these companies that that Elon Musk wants to go to Mars and wants to go there. That means Elon Musk somewhere is thinking nuclear reactors. And I look at that environment and I go, that's a different environment. And one of the things in the cyberpunk dystopia that I think about that, in reading and other things, is transnational corporations armed with nuclear weapons or armed with, with the capability to develop nuclear weapons. That seems like something we should avoid. That seems like something that's not great. But beyond that, it's a development standpoint of, I think, I got into space nuclear power because I wanted to see us get into space. I got into space nuclear power because I'd like to see us develop things. And I think that competition is healthy. I think that having different players is good, but LEU really becomes enabling and necessary in that environment. So let's move on. So if we look at a space nuclear reactor, I'm going to skip forward here really quickly, but so if we look at a space nuclear reactor, you are in general looking at a system where you have a core. The core is LEU or HEU fueled. It produces heat. You have a reflector. I'm not going to go to why you have a reflector, but you're going to have a reflector. You're going to have a shield. Your shield is necessary. Space nuclear reactor is producing radiation, so you're going to have to shield your power conversion. You're going to have to shield your astronauts. You're going to have to shield your payload. So you're going to have a shield. Then you have some form of coolant. You have power conversion, and you have some radiator. The reason I say this is that all these components contribute to the mass. And we'll come back to those in a second. So moving on. So if we look at kilowatt class space nuclear reactors, and I like to think of the kilowatt class reactors as being entry-level reactors designed to bridge the gap between where the RTGs, the simple plutonium-238 systems we've been using for decades are, and larger space nuclear power systems, hundreds of kilowatts to hundreds of megawatts, where RTGs aren't an option. And if you look at kilopower, it's a very simple system in that it basically looks like that schematic. You have a uranium molybdenum cylinder, you have a control rod in the middle of it, you have a reflector surrounding it, and then you have some way of bringing out the heat, and then you have the shield above it. For our analysis with Leonardo, we'll go on to the next one. We simplified this even further, and we made it a simple cylinder with a hole in the middle of it and a reflector on the outside of it, which is what we used for all of the analysis that we did. And now is where I'm going to be really pained, because I went at recommendation, simplified this, and then promptly sent the wrong presentation. So now there are twice as many equations as I was recommended I present. So if we talk about a reactor, the thing that you are interested in is criticality. If you can't get a reactor critical, it isn't a reactor, it's just a big block of uranium that's going to do very little other than sit there. To get critical, there's a measure of that, and it's called multiplication factor, or K effective. And this becomes really important for the discussion of LEU versus HEU. In order to have a reactor, you need a K effective greater than 1. Usually maybe something like 1.035, well, that varies based on design, but something greater than 1. And if I go to very, 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 very simple nuclear physics, this is a matter of sort of 3 factors. So we're going to ignore eta. It's the number of neutrons produced by fission. I had taken that one out. Fission is the probability that fission happens. This term here, which you can ignore other than saying that it's a term, is the chance that a neutron gets captured, or doesn't get captured, actually, is what the 1 minus. And then this is a term that the neutron escapes from the system. And you need these things to end up being about greater than 1. And it turns out that the probability of fission, to a very, very rough approximation, is based on the amount of uranium-235 you have and the cross-section of the 235. Likewise, capture is roughly proportional to the amount of things that aren't uranium-235 that you have times their chance of capturing. And probability of escape is basically inversely proportional to size. So moving on.
You'll all get MA degrees in nuclear engineering
Yeah,
at the end of this class. Certificates.
Only if we pass the quiz.
Yeah. So if you go to a lower enrichment, enrichment is basically the ratio of 235 to not 235, or to 235 plus not 235. So if we drop our enrichment, this number goes down. So that N235, so your probability of fission goes down. Your probability of capture and other things goes up. Your probability of escape, if it doesn't change, if the size doesn't change, it stays the same. So your K effective goes down. So the simplest thing, in your simplest case, is you go to LEU, and it means a bigger reactor. You have to either make the reactor bigger, or you have to add more reflector. So you've dropped this, you've increased this, so size has to go down, or size has to go up, so the probability of escape goes down to maintain. Now, if we look at the consequences of this, and modeling this, and this is a roughly kilopower style reactor, you notice that if we just swap out the system, K effective goes down a lot, and it's not even viable. You can try adding more reflector. You can't get there with more reflector. So you end up having to go with more size in the core. Next one. And so we end up, we add reflector, we add core, we make a bigger reactor, and yeah, this will work, sort of. It'll work in the sense you can get critical. It'll work in the sense that, you know, you can probably operate. On the other hand, it's now 15 times heavier. That went from 100 kilograms to roughly 1.5 metric tons. I think everyone would agree this is non-viable. This is not a realistic space reactor. So, and it turns out, first thing is that, all right, well, we can play around without changing anything else. We can play around with reflector in the core, and it turns out that putting the thickest reflector on it possible isn't necessarily the lightest option. We can play around, and we can trade, you know, core size for reflector size and vice versa, and we get it down to about half that. So 7 kilograms, that's better, but we really can't get to something that is a good comparison to a kilopower style reactor. So what we do is we add moderator. Now, a moderator changes this number here. So if we add a moderator, your probability of fission goes up. Incidentally, your probability of capture probably goes up too. You're hoping this goes up more than this does, but it allows your size to go down. So if we continue on. So it's a standard technique. Almost all commercial reactors are moderated reactors. And almost all commercial reactors are moderated water reactors using water today, because there's really 3 reasons. Water's cheap, we understand it, and it works. However, we don't really understand it as well in space, partly, although, you know, we do, but not as well as we do on Earth. But it limits your operating temperature. And in space, we're really hoping for a high operating temperature, very high operating temperature, which water is not going to work. And so that pushes us to things like metal hydrides. Metal hydrides, zirconium hydrides, the reference. Hydrogen is what you care about. It's higher operating temperatures than water. You could go beryllium and graphite. There are some other things in development. But when we add a moderator, we can continue to push down. So we're just pushing this number down, balancing moderator. This one is 30% moderator, so 30% moderator by mass, 30% or 70% fuel. Get lower. That's the best we can do. Homogeneous. We did study whether or not by doing different configurations, you could get lighter systems. And you certainly, you know, we looked at things like spheres of fuel suspended in the moderator. We looked at alternating plates of moderator and fuel. We looked at the sort of innovative sort of DNA-looking design that you know, we thought might have better heat transfer, better properties. it looks neat. It's kind of cool. It isn't better enough to make it worth the effort. But if we balance all of these things, we can push down and we can get to about 193 kilograms. Now that's about twice what a kilopower system might be. That's, that's getting there. Now there's problems. There's actually several problems. One of them is that you've managed to push down the amount of fissile uranium. So you're pushing the amount of fissile uranium down, which means your lifetime is likely going down as well. So going to the next one. So as we're burning, as you're using your reactor, it's consuming your fissile uranium. One way you can look at that is that you're removing your enrichment. What you're actually doing is you're reducing your 235, and then of course you're increasing your things that are not 235. So K goes down as you operate, and it goes down inversely proportional to the amount of 235 you have in the reactor. So the less 235 you have, the faster that number goes down. So we did some work on looking at how minimizing the reactor through moderation shortens lifetime. And if we plot some of that out, we see that we went from our HEU reactor, which from a fuel standpoint has an essentially infinite lifetime, or very, very long lifetime, comparable to what we're seeing in Voyager. But then if you go to your really highly moderated system, where you've pushed your uranium-235 down as far as you can get, we're now looking at a system that probably runs out of fuel in 7 years, 7 to 10 years. That's may or may not be good. But a little bit higher enrichment, yeah, we can get there. Or not enrichment, a little bit more moderation, or a little less moderation, so you have a little more uranium. We get there. Now, that being said, we've left off at least two big things, and I'm sure people will tell me of others. There's two that I've identified. One is shielding. So the radiation shield, included in our mass estimates, I didn't include the radiation shield at all. And I've got other work that we've done, and we often sort of neglect the radiation shield. But it turns out that often the heaviest thing in your reactor system is your radiation shield. And the bigger your reactor is, the bigger your shield is, and often it's a factor of a square. Because your shield has to surround your reactor, and it's round, and so as your reactor diameter goes up, the shield goes up much, much faster, and so you get much heavier. And it turns out from some work that we're still working on getting published that for moderated space reactor, you don't get any real advantage for moderated, low enriched. There were some speculations that the people have had that maybe a moderated reactor will need less shield than a fast reactor. What you see in the space reactor regime is you're really not, or what we see so far, is you're not in a regime where the shield is any lighter. And in fact, surprisingly, and this is one of the reasons we're still working on this paper, is in fact, it looks like it may be worse for reasons that we're still trying to figure out. It's interesting, but it's not better. The other thing is that I completely left out materials. And anyone who, material issues, anyone who's been dealing, or anyone who's been involved in space reactor development for any length of time knows that materials is what kills you. That was what the SP100 program, I was involved in the Amtech program, where we sort of started off without figuring we just solve the materials eventually. And SP100, in a lot of ways, got into trouble and didn't finish because it went to materials that didn't exist. We had to do. Materials development is complicated, it's expensive, it's hard. And I completely ignored all of that in this analysis. And the problem is that while we have moderator, and we have zirconium hydride, we certainly have used zirconium hydride, and we have experience with zirconium hydride, it's not in the regimes that we're talking about in this space reactor. So trigger reactors, research reactors, a lot of universities have them, I won't say most, it's actually a handful at this point, are zirconium hydride, but they're operating at below boiling. They're room temperature reactors versus 1,000 Kelvin reactor where you're trying to push the temperatures up as high as possible to get the best conversion efficiency. And certainly people have noted that SNAP-10A was a zirconium hydride moderated reactor, but the power was low. It was less than a kilowatt, half a kilowatt of electric power, and the lifetime was short. Now, it was supposed to be longer than 43 days. 43 days was because there was a voltage regulator failure on the spacecraft that had nothing to do with the reactor, shut the reactor down. But it was still not intended to be a 10-decade or a decade-long power system. And the problem is hydrogen diffuses. Hydrogen diffuses well, diffuses at high temperatures, and the issues of how hydrogen is going to behave at high temperatures, how we clad our zirconium hydride, how we integrate our reactor, all of these are key issues that in order to get there, we need to consider. So to summarize and conclude, I think there are some compelling arguments for why we eventually are going to want to look at LEU for future spacecraft systems, especially if we start looking at international development or corporate or commercial. These are regimes where I think we want LEU systems. Switching from HEU to LEU is almost certainly going to increase mass. How significant that is depends. Moving to moderated systems gives you the opportunity to reset that mass penalty. And I think if we're going to look at LEU reactors, we're probably talking moderated systems. But we have significant research hurdles in terms of high temperature moderators. We don't have the materials knowledge that we need to be able to do this in the near term. We need to understand metal hydrides better. We need to figure out our claddings and diffusion barriers for hydrogen. And we need to figure out how to integrate these into our systems. Now, it turns out the bright side of that from the space side is this is exactly the same kind of questions that we also need to solve to push out of the high activity, low enriched uranium and microreactors. So there's also a parallel push that was in the NEOP call this time around for figuring out how to reduce the enrichment levels in the microreactor world. Microreactors are a lot like space reactors, honestly, the terrestrial space reactors. There we're starting with HE, high activity, low enriched uranium. But again, there's a push to get down to reactor 5% enriched LEU. So that.
Thank you very, very much, Jeffrey.